Okay, last lecture we talked about potential energy and I said that you must derive this, and I have done this for you. I've said that potential energy is eventually given by mgh if you take h1 to be 0. And then I left you with example number 7. Okay, example number 7, I asked you all to go back and try it. Right, as very good students, as you know, I've been a student too. When the teacher say give me an example, I definitely go and try it. I know you have done the same thing. So let's look at the answers now. Right? Maybe I should just go through about what the question is again. So you are doing chin-ups, right? So you're doing chin-ups. And okay, sorry about that. Alright, so you're doing chin-ups, and the person weighs 700 Newton. Actually, this is a common misconception. A lot of people say, I weigh 6 kg. No, that's not your weight, that's your mass. Right? So this guy weighs 700 Newton, excluding the weight of the arm. So during the first 25 cm, right, of the lift, each arm exerts an outward force of 355 newtons, that is a total of 710 newtons. If the outward movement starts from rest of the person's velocity at this point, at the 25 cm mark, after it raise itself up of 25 cm, right, about half about 90 degrees, what is the person's velocity? So here, you have understood about work, you have understood about TPE, and some fundamental point of conversion energy. You should realize this, that the work applied by the arms will be the force, total force, multiplied by the distance, we give 177.5 joules. The gain in TPE is actually just 700 times 0.25. You realize that the work equation is actually the total work done must give you the gain in PE and KE. Right, there's no other energy involved. You sub in the values and equation. So KE is half mv squared, half m. Right, so here this is a common trap that students fall into, that they know that this 700 Newton, they forgot to convert it back to mass. Right, v squared. You realize that the v is about 0.265. That's about 26 cm per second. Sounds just about right, in terms of the speed. So here there are two things that I want you to take note. Those that tried it, you have made these mistakes. You may have forgotten about gravitational potential energy. You equated work done to the gain in KE only. You left out this PE, and you have had some incredible velocity. You'll be moving up at a speed of a bullet. It's not possible. Okay? Right, by the number of people I see copying, I'm sure you all have tracked this question very well. Right, so we can move on. No? How many of you heard me say, try this question at home? How many of you did not? Okay. Okay, ready? Are we ready to go? And go. We've got a lot to cover today. Too slow. Right? I need to introduce to you what is conservative force and non-conservative forces. Summary. Everything that's not behaving like friction, it's a conservative force. Okay, at least in A-level syllabus, most of the time they exist. Okay, so conservative force, I give you an example. This is my water bottle, right? If I raise it from this point of the table to the top of my head, okay, in this way, see how like that? Okay. First method. Second method is like that. And then here. Third method, I send this by DHL to Paris, to Europe, through Russia, and back to Singapore and put on my head. The gain in GPE is it the same for this bottle? In all three methods is it the same? Yes, right? Because GPE is provided by gravitational force, and gravitational force is a conservative force. That means, in summary, they don't care about the path you take. Okay, your path can be very meandering, go to the end of the world and come back, whatever. The gain, the work done, again the GPE and the work done is the same. So this holds true for gravitational force, electrostatic force, which is for a charged particle, and for elastic force. Right? That means a rubber band, spring, etc. So these are examples, right? Same thing as I said. In weight, we have a derived gravitational potential energy using this method. We say that the upper force we need to do to move this object from x to y through this distance delta r must be equal to the weight. Right? That's how we prove and derive gravitational potential energy. We said that the force you must apply to move it through this distance of distance w, right? And hence that is the GPE. And here, right, the potential energy gain is just work done with W times delta. Right? But this can be generalized to any forces. Right? If this is a charge, right, and this is a plate, this is a positively charged plate, this is a negatively charged. A positively charged object, and this is a negatively charged plate, this object is attracted downwards. But to shift it up, I must apply a force. Okay? Just that whether this force is constant or not, we don't know. Right, so this is what we have done earlier. But one of the generalizations is this, right? Is that the change in potential energy is external force times delta R. And we know that this F, this external force you must apply must be equal to negative. That means to move the object from here to here, you must apply external force. And to apply it without gaining KE, this external force must be equal to negative F. Am I right? Are you lost? Alright, good. You are very responsive, so I shall credit you for that. One more time. To move this object from point X to point Y, and assuming that this object is experiencing a force F, that means this water bottle, right, will always experience a force at this point or this point. I mean, when I let go of my hand, right, due to her. To the gain in the potential energy of this object as I slowly raise it through this distance must be provided by the work I do, which is external force. And there's an external force I must apply here to raise it from here to here. If not, this object will start to accelerate downwards. So the work I do is equal to the gain in potential energy. And the force I've applied must be equal to the negative of the force this object experiences. That means the opposite direction. Negative of this F, opposite direction. That means equal magnitude, opposite direction. And I realized then that the force that I must apply, the force felt by this object is negative delta U delta R, which means that F is equal to minus dU dr. I've done some crazy mathematics there, right? From here to here, the math teacher will kill me, but my physics it makes sense, right? That means for incremental changes in R, right? And if I know the delta R, I know the delta U, that means the gain in potential energy, the change in delta R, I know that the force is material. feeling at the point of time is equal to F. This will help you in many of the chapters that follows this. Any of the chapters that uses a conservative force, this will help you. Okay? That means chapters like gravitation, chapters like electric fields, chapters, magnetic fields, but not that you're doing a lot of that. So electric fields, gravitation, these two will help you a lot. This equation will help you a lot. Okay? Right. Moving on. So just to give you an example. You agree that if I plot the potential energy that this bottle has in relation to the height it has from the table, if I lift it up by 10 cm, the energy is 1 unit, 20 cm, energy with 2 units, 30 cm, energy with 3 units. Agree? It will be a straight line like this. Then if I give you this graph and ask you, what is the force felt by the object? What is the gravitational force on the object? All you have to do is do this. Right? If you take upwards to be positive, that means as your GPE goes higher and more positive, you realize that the force, if you differentiate F equals to minus du dr, it's just negative mg. Because you know that U is equal to mg. Okay? Sub this in, differentiate, you get negative mg. That means the force, or the gravitational force acting on this object is negative mg, and the direction is down. Right. So I can give you a straight line. I can give you a curved line. It does not matter. As long as I give you a energy to distance graph to find the force acting on the object at that point of time, all you have to do is to differentiate and find the gradient. Multiply the gradient by a negative, and you get the value of the force. Okay. Other than this simple application now, if I show you any others, you all will be very, very, very confused. So I leave it to the teacher to do gravitation and electric fields. Okay, just keep this in mind that you can differentiate energy. You can differentiate if you're given an energy distance graph. You can differentiate to find the gradient, to find the force. Right? So one of the other examples that we also have gone through before, so that was for MGH. The other one that you actually know by now, which actually example is actually this. You know that I've given you, and we have worked through before, right, the lecture on forces. I heard some very interesting lecture in that. He showed you that the potential energy is half kx squared. Oh, I really don't have one. Anyway. Potential energy is given by U, and that's given by half kx squared for a spring. Right? For a spring, for an elastic object. U equals to half kx squared. If I want to ask you what's the force on the object at the point of time, all you have to do is differentiate this, and you realize that the force is equal to negative kx. That means the force is variable. The further you are away, the larger the force. Okay? Remember this? In that chapter, I told you F equals negative k, and I proved to you, that the energy was half kx squared. I worked it through. In this lesson, I'm doing the opposite. I'm giving you this is the energy. I can work it backwards through this concept that force is equal to negative du dr. And so you can go forward, you can go backwards. Are you all lost? Who is not lost? Oh no. What can I do to make you not lost? Show you the way. Let me give you a very good signpost. Okay, if you are lost, this is what you need to remember. See where my laser is going? This is what you need to remember. What you need to do for any potential energies given to you, just differentiate, you find the force, and that's that. Okay, that's that. Never mind. I expect at least 60-70% to not. Yes? Sorry? Is from this part. That the gain in potential energy, right, is the work I have done and applied on it. The work I've applied on it is the external force times the distance r that I move. The force that I apply on the external force must be equal to negative m because it must be equal in magnitude and negative in opposite direction. With this, and with a small enough delta r, I can say f equals to negative du dr, but the delta r is very, very, very small. I can say f equals to minus du dr. So this is how I prove it. Do you need to prove it? Actually, no, you need to apply it. So if you are not sure how this is derived, you need to apply it. Okay? At least be sure of how to apply it. So I have applied it for gravitational potential energy. I applied it to elastic potential energy. And I derived for you the forces, and it makes sense because it is the forces that you know. Weight is negative downwards, Hooke's law is negative here. Okay? So these are for conserving forces. This is only true for conserving forces. For non-conserving forces, it's a different story. What is a non-conserving force? It will be what you call friction, air resistance, and drag in water. Right? These are dissipative forces which result in energy loss. Examples I've already mentioned. Okay. So I've highly summarized the dissipative forces because no point going through a lot of theory. In the end, right, you just need to know what they are and how to apply it in the equation. So there you go. Oops, what is it? Let's see if this works. Do you hear the sound one more time? Important, why you? I don't do things for nothing. So you stretch the cord and you put an arrow there, just like Hunger Games. What cat means, right? Okay. You shoot the arrow up. There is a K in the arrow. Do you hear the sound? Okay, one more time. Shh. Okay, quiet. Shh. If you don't keep quiet, you'll miss the sound. Right, so what is this? This is a transformation energy, right? One side to that carry. I always wonder why Legolas never run out of arrows. Okay, anyway, transfer of energy. So this elastic potential energy in the cord was transferred to kinetic energy in the arrow and some heat energy, right, as it passed through the air. What about this? What is this? It's a match. Very good. It's a okay. You strike it, you transform into light and heat energy, right? What about this? The chemical energy in the battery is transformed into electrical energy in the circuit, and then in the light bulb is transformed into light and heat energy. Yeah. There is also conservation of mechanical energy. Mechanical energy, so this is new to you. What is mechanical energy? Okay, mechanical energy is a sum. It's a sum of kinetic and potential energy. Right? And if it is conserved, that means your total initial energy must be equal to your total final energy. Okay? And your total initial will be K initial plus potential initial, K final plus potential final. Right? So if you refer to this as the potential as in potential energy due to gravity, you can actually have the equations like this. Okay? So this is one of the equations that you commonly use to solve your questions, your problems given to you. But I want to suggest a different point of view, right? So all look at the screen, look at the screen. This tells you what is the total initial energy, and it says that it must be equal to your total final energy. But can I do this also? I can say the loss in the GPE of the system, that means if this is a bottle, the GPE that lose must be equal to the KE gain. Is that correct? Yes, it's true. So there are two methods to present any energy equation. This or this, right? Total initial energy equals to total final, or the loss in one part becomes the gain in another part. So you can use either of these. Personally, I prefer this a lot more. Okay, personally, I prefer this a lot more. Oh, yeah, good. So these are for the people who like stuff, who like to watch videos. Why is there no music? How many of you want to do this? Okay, let's. So this is what? What is this? This is a conversion of potential energy into kinetic energy, and as it goes on the other side, kinetic energy is converted back to potential energy, right? But because it's a real life situation, there is also air resistance, right? What? Go and search yourself. There's so many nice videos out there. So, some crazy rock climbers go and try this. A word of caution, don't try this in any rope. Right? To actually do and finish the rope, you need to do some physics calculation. Seriously. Alright, you will learn it in circular motion in the next chapter. Next chapter. Right? The forces withstand by the rope is actually quite important. So to actually do this safely, you don't want anyone to then right? You swing so happy, then the rope break. Then very not happy. Right? So you really want to do the physics well. Physics is very important. Okay. Oh yeah, so actually this picture, this is just about conservation of what energy. In this whole picture, if there's no heat loss, no air resistance, it's conservation of what energy? Mechanical energy, mechanical energy. Alright, so here's an example. A child and a sled with combined mass of 50 kg slides down a frictionless slope. If the sled starts from rest and has a speed of 3 meters per second at the bottom, what is the height of the hill? What is the height of the hill? Right, so why don't you try it?
Alright, alright. So this is a simple conversion of energy. However, right, so this is like secondary school, but seriously, don't copy everything. Just copy from this line onwards, because I show you how I do it. I use a word equation to say total initial mechanical energy equals total final. I give you the equations, which mgh equals half mv squared, and I sub it in. Most of you should have gotten this answer, right? Because this is seriously a secondary school question. Right? The answer is 0.459. It's just a warm up, right? Just a warm up. 0.459. I'm not going to stay very long because you should be able to do it even without looking at my answers. I want to show you, however, my alternate solution. I skip through a lot of parts. I just say the change in mgh equals to gain in ke, and I find this same answer. So I like this answer better. Number 10, example 10, in the dangerous sport of bungee jumping, a daring student jumps off a balloon with elastic cord attached to him. Right? The unstretched length of the cord is 25 cm. That means as he jumps off, as long as he does not fall more than 25 meters, the cord does not stretch. Right? It's an unstretched length of 25 meters. The student weighs 700 newtons and the balloon is 36 meters above the surface of the river. Calculate the force required, the force constant K of the cord if the student is to stop safely 4 meters above the surface of the river. So one of the skills in physics, right, is to convert a wall of text like this into a picture. Imagine a video, right? Just now you have seen the people jumping off the cliff with a rope attached to them. Same. How would it look like in a video? The person will be at a balloon, he will jump off, and he'll reach the bottom 4 meters above the surface of the river. Alright, so it's a balloon 36 meters above, jumps off. And then you draw it as a diagram into your answer. So most of these questions you need a diagram. Right, and then you want to attach, because this question you know is obviously a conversion of energy question. You lose gravitational potential energy, but you must gain other forms of energy. I ask you one simple question. At the bottom of his jump, 4 meters above the surface of the lake, is there kinetic energy? Is there kinetic energy at the bottom of his jump? Is there? Say no, right? Because if there is kinetic energy, it's not the bottom of his jump. Okay? So, if you jump down, you lose GPE, you don't gain K at the bottom of the jump, what do you gain? You must gain elastic potential energy, right? So, using my method, right, which is what I prefer most, the loss in GPE is the gain EPE. All you have to do is do a 3-liner and you have your answer. Okay? So it's relatively simple. The only difficult part is this, that students commonly make mistake is this. They think that the x squared is 32. It's not. The x is the extension of the bungee cord. It's not the distance that you move through. So it must be 32 minus 25. So this one you must remember. Strong hint. This one you must remember. Hint. Alright. Okay. Until now, it's still pretty simple. Loss in GPE become gain in K. Loss in GPE become gain in EPE. Very, very simple. Is there anything a bit more difficult? Yes. It is the questions that involve non-conservative forces. That means you include friction, include air resistance, include drag, whatever you, right? And the total mechanical energy will not be conserved. There will be losses due to these forces. Right? And these forces are sometimes useful because if I roll a ball on this carpet grass, I want it to stop so that I can pick up the ball, right? If I roll the ball and it doesn't stop, that means there's no dispute. The ball will keep rolling and rolling until Paris, right? Which I do not want that. So, once again, this is the equation to think about. The total energy loss in one part of the system, usually GPE, right? Must be the total gain in another part of the system plus work done against resistive forces. So let me give you the first example. A diver, 70 kg, steps off a 10-meter tower and drops from rest. The keyword here is from rest, that means at the top. Does he have KE? Answer is very good. He comes straight down into the water and he comes to rest 5 meters beneath the surface. If it's 5 meters beneath the surface, can I ask you, how much GPE did he lose? mg how many? The h is how many? 10? 15? 5? Read carefully. Is it 10, 15 or 5? Right? And then at the end, at the bottom, what kind of energy does he possess? Does he have KE? If it's at the bottom, does he have KE? No. Does he have GPE? Well, if this is the bottom, you take this GPE to be 0, he has no GPE. Then what energy does he have? He has nothing. So if he has nothing, the energy might have gone somewhere, right? Energy is lost due to the resistive force exerted by the water on him. So his initial energy all gone due to work done by resistive forces through a certain distance. Does the resistance of water act on him above the water? No, right? Obviously not. So try out this question. Take 1 minute. Okay, let's see. So this is the thinking process. At the initial position, the P is 0, at the final position P is 0, so there's no energy. Okay, so fine. So working is simple. The loss in GP must be the gain in KE plus work done against release. For the gain in KE must be obviously 0. So you have a very simple equation. Loss in GP is a work done against friction. You realize that in physics, the difficult part is not the calculation. The calculation is so simple. The difficult part is coming out with the equation. And some of you are stuck, right? Not coming up. So you must learn in the lecture how did I decipher it, which is this, the thinking process. You think about what forms of energy are there, what forms you don't care about. And then all you do is just quick. So it is easy. You let R, because R is what you need to find, is the release force times the distance. But here is where the other trap happens. A lot of students will write mgh equals 10, the h equals 10. And that's not true. Because you lose 10 meters before you hit the water surface, but you will lose another 5 as you go into the water. So you lose a total actually 15 meters of height, which means that the total reducing force is 2.06 times 10 to the power 3. Right? mgh divided by the total 5 meters in which the force is acted on. Alright, we need to speed up. Copy faster, we need to speed up. Right, in this example, a bag of this mass slides down a tube, right? This is the length, this is probably what happens to the airport. It is 8 meters and inclined 30 degrees, it reaches at the bottom of the tube with a certain speed. But if you calculate it, the total mgh loss as a result, this height will not equal to, will not give you this kinetic energy due to this speed. That means sum of the energy is lost. Okay? So it asks you what the average frictional resistance exerted by the tube on it. Well, once again, let's look at the thinking. Initially, there's di is 0, after that, there's O6. Oh, that means my equation must involve both GPE, KE, and work done against friction. So there you go. Loss in GPE must be gain in KE and work done against. You realize that now the KE is not inconsequential. You need to, that means it's of consequence. So mgh is here, the change in KE is here, the work done against friction is here. You realize that in the examples that are given to you, I add on and I make the examples more and more difficult slowly. Right? So if you read through examples, you see the evolution of the typical theme of the whole lecture series. Bring all the numbers, you realize it's one equation, one unknown, you have f equals to 1.6%. Right? So once again, the difficulty is in forming the equations. Right? There is an additional difficulty here, which is to resolve to find the vertical height lost. And it's sine 30 degrees. But by now, it should be quite. It should be quite easy for you. Okay. Right, you all have this, right? As the given to you. So you can try example 13. Any questions on this one before I go to 13? Okay, moving on 13. I've been giving you something that falls from a high height to a low height. High to low, high to low. Can you go the opposite direction? Answer is yes, you can. Right? This is what actually happens in a submarine, right? When you're a submarine, you're trying to launch a missile up to the sky. You must launch it with a certain velocity so that it can pass through your skin. You don't want to have your submarine break the surface of the water and then launch the missile. Because what's the whole point of submarine if you need to break the surface to launch the missile? Right?
they get shot down by a fishing boat. A fishing boat with RPG will shoot you down into the surface through the water. So you don't want, right? You want to shoot the missile while you're still underneath the water. So the question is this velocity enough to shoot it out of the water, such that it still has enough KE at the top? Let's say you already know that, so you have to do some calculations. And this is the question if you are an engineer calculating the velocity of the missile. So there you go. It's projected with 180 meters per second, 150 meters below the surface of water. The water receives 200 newtons of drag force. What is the velocity right before it leaves the water? So you must think about it, right? Thinking, okay? Initial is 180, final is what you need to find, so I put a question mark. You say, okay, what is the change in energies here? What energies here involved? Is there only friction? Is there any other energies involved other than KE? KE, friction, and what else? PE, very good. Right? So loss in KE equals to gain in PE plus work done. Notice here that I've swapped the initial equations because the loss in K is the one that's giving away the energy. Then you have half m initial velocity minus half m final velocity. This must be the gain in GP plus the work done against friction. Since you know the initial velocity to be 180, this is not a problem. Vm is what you don't know, but never mind, you're doing everything except for that. Potential energy, you know everything because you need to cross 150 liters of water. MPH must be mg 150. The friction is also given to you to be 200 newtons. Multiply by the distance of 150. One equation, one unknown, is very simple math. Answer should be 169 meters per second. Okay. So you realize that actually the difficult part is only in the conception, right, of the equation. Otherwise, it's actually very simple, very direct. In fact, if you see a work energy power equation in the A level, you should smile to yourself and say, yes, I got it. Huh? I've armed you with enough knowledge. If you have read through the lectures, right, you can do the tutorial. If you can do the tutorial, you can do A level. No problem. Right. Let me give you an overview of energy problems. I'll look to the screen. If this is your initial total energy, this must be your final total energy. Okay? There is a conversion in between. Let's say your energy is given by initial K and GPE like this. It will then become final K and GPE like this. That means the KE gain is due to the GPE loss. Simple enough? Yes, huh? Now, I can generalize it to different energy types. It will not be K and GPE. What if it looks like this? What if you have less final energy and more initial energy? That means in between there must be some energy lost. Right? Some energy must be lost. But what if your picture looks like this? That means you must have put in some work done by external body, plus the initial energies converted to become some final energies and some energy loss. Okay, and this is also another point. Did I tell you? My French professor said this is a $10,000 equation. You spend $10,000 to learn this. So there you go, $10,000. Happy? Seriously, I'm not joking. This is what he said was $10,000. Right? So I repackage it for you. The input or the work you have done to a system will go to the energy of the system. There will be transfers of energy in various forms, so and so forth. There will be some work lost, some energy lost to the friction, and the rest will be desired work. Alright? The rest will be desired work. $10,000. Just that. Alright? There you go. Next. I've completed everything to the left. I'm going to talk about power. In power, there are three things to take note of. Power is a rate. It's a rate of something. Rate of work done or rate of energy transferred. Power is measured for two kinds of power, instantaneous or average. Okay? And then it's used as a measure to calculate bond efficiency. There you go. This is the definition. You have no choice but to memorize it. Power is defined as the rate at which work is done or energy is transferred. The unit is called watts, capital W. I'm going to spell it like WATS. And work is done over a period of time. The average power is delta W over T. Delta W over T. Okay? Right. And instantaneous power will be dW dt. What's the difference? I'm going to show you. I'm going to do work to move this water bottle from here to the end here. Right? In the 3 seconds that I moved it, I had high instantaneous power, some instantaneous power. But if I average it out over the whole period of the lecture, is my power very high? No, because I take a long period of time, my instantaneous power is actually very low. Okay, so that's the difference between instantaneous and average. Right? Instantaneous happens for a specific time, 0.0, the first 1 second, the first second, 1.2 second, at time 1.1 second or time 1.2 second. Alright? So, for constant force S acting on an object at velocity v, the instantaneous power, this is the derivation. If power is the rate of change or conversion of work, if you're going to talk, you need to talk softer, right? Work, right? The work is given by Fx. If S is constant, it's just dx dt. So F is just Fg, right? P equals F, dx dt becomes G, so P equals Fg. That's instantaneous power. That is, the power is given by the force multiplied by the velocity at that point in time. Okay. If I want to find average power, it's just the force multiplied by the average velocity. Okay. Average velocity. So here's an example which is pretty difficult. Hope I did not. I need to give you the answer straight away. Here, this is a heavy car. Starts from red and x-rays uniformly to 18 meters per second. That means it's moving to the right. Okay. Air resistance remains constant, that means there's air resistance. So if you look at the force diagram, I realize that the question does not have a force diagram. We should draw it in. The force to the right is by the car, air resistance to the left. Find the average power developed by the engine. And to find the average power, you must find the force first. Can you find the force? To find the force, you know that F equals to ma. Do you have m? Yes. Do you have a? Yes. Right? So to find the average power, you need to find force. Then you need to find average velocity. Right? So there you go. To find the acceleration, a equals to this, the rate of change of velocity. The force of the car, however, right, the force due to the car, right, is T, air resistance is R. The net force is T minus R equals ma. Right, which means that the force of the car must be resistance plus ma. This question is not as easy as it seems, right? Because I'm giving you the answers. It may seem easy, but please put a star, come back, count out the answers, and try it again on your own. Okay? Tension, not tension, thrust. The force given by the car is 400 plus all this, giving you this amount. So to find the power, all you have to do is take this value, the force of the car, multiplied by the average velocity, multiplied by the average velocity. But do you have the average velocity? No, but can you find it? Yes. So you can find the average velocity. Okay. I count down 10 seconds. So once again, to find the power, the average power provided by the car, you know that P equals to Fv, we know that F is equal to ma. given by these two problems, the F, however, must be more than L resistance to give a certain acceleration. So the force provided by the car is the resistance plus acceleration, because you know that the net force. Okay, this is the difficult part. Without you may not comprehend this, this is the more difficult part. But otherwise, once you have this, it's relatively simple. Average velocity is given by this, because the final is 15, initial is 0, it's a constant acceleration. Average force is just 9. So average power output is just force times velocity, is equal to 2.39 times 10 to the power of 4. Okay? Alright, the next part asks you for the maximum or instantaneous power output at t equals to 12 seconds. So your instantaneous, is the force the same? For instantaneous, is the force the same? It must be the same because it's constant acceleration. It's the acceleration doesn't change. If the acceleration does not change, the force must be the same. However, is the power input by the car the same? Answer is no, because power is Fv, right? The F of the car is represented by the T, represented by this letter T here. The velocity at time equals 12 is 15 meters per second. So all you do is power is Fv, G is 18, so everything in, we get this answer. You notice that this power is exactly twice of before, right? Twice of before. Simply because the velocity was doubled. The force is constant, the velocity is doubled. Okay, moving on. We need to have some idea of what is efficiency, right? Basically, you have learned about it. How many of you have learned efficiency in secondary school? Very good. Some of you. Who has not? Oh, one. Okay, can you stop that? Not funny. Efficiency, right, is the useful power output over the power input. If you have more power output than power input, you have won the Nobel Prize. Just remember that to quote that your physics teacher is the whole. Right? Another way to represent efficiency is actually the power output over power input. Once again, you cannot have more power output than input. Cannot. It sounds like a scam. So in example 15, you are having a drum, right, of radius A, radius 0.5, winding a cable. You are winding this way. So those of you who have lived in kampongs before, you know how a well works, right? You have a pail that's deep inside the well. As you wind this thing, the pail will come out. Okay, you wind this thing, the pail will come out. So I know many of you live in kampongs, huh? So radius is 0.5. At least you have seen a movie, right, about kampong. The load is 50 kg, quite heavy, right? And this is by fully B. You rotate this electric motor at 20 revolutions per minute. the time taken to rise through the height, find the time taken to rise this through a height of 30 meters. Okay? So the first part I already gave to you. The time to rise 30 meters. Right? So this is simply just velocity equals to distance and time, right? So if time equals to distance divided by velocity. Right? For kinematics, you already know this. Time equals to distance divided by velocity. The velocity is 20 times of the perimeter. The velocity is just simply 20 times of the perimeter, 2 pi r. So here's the funny thing. I have students coming to me in JC1 and JC2 telling me, sir, I forgot what's the equation for perimeter of a circle. Okay? Because you all learn so much other higher mathematics, higher things, right? You forgot what's the perimeter of a circle, you forgot what's the area of a circle, you forgot what's the area of a sphere and volume of a sphere. Please go and remind yourself what this is. Anyway. You'll convert this and you'll find that the time energy is minutes and then maybe you convert it to seconds. This you already have. The second part is asking you, what is the work done by the motor? If 30% of the work done is lost, that means you need to put in more energy to achieve this gain in PE of the water of the 50 kg mass. Okay? So if this is the efficiency, you simply have eta equals to 0.8. And we know that power output over power input is equal to 0.8, so we can rearrange to write this thing. So simply, right, the energy that you have, the energy gain divided by the time is the power output. The power input must be more than that, you divide that by 0.8 to get a larger power output. Right? You get a larger power input. This is a power input by the electric motor. Right, you realize that the power input must be more than the power output. So this is what I taught you. In the first lecture, I taught you about work and energy. And this lecture, I taught you about energy and power. So back to this. At the start, I said, right, how do you describe Usain Bolt? Does he have a lot of force, a lot of work, a lot of energy, or a lot of power? A lot of forces? No. By now, you must be able to say this that he probably possesses a lot of energy, right? And he can convert this stored energy into work. So he can do work to run very fast at 15 kg. He can do it at a fast rate also, so he has we call him a high powered individual. Right? He also probably does it at high intensity, so he doesn't have wastage of energy. Okay? So I hope this gives you a better picture of how to talk about objects in real life. Okay? Alright. Thank you and have a nice day. Bye bye. See you next year.
The last part is wrong.
Oh, okay, can, thanks. Just change it off. It's a minor calculation. I will change it later.
The whole class copies.
This one?
The whole class copies are
Oh, you help me tell them? It says a calculation thing. It's not a conceptual mistake. I'll just change it later. Thanks.
For example 14, right? I'm sorry.
I have to clarify something, right? You went to find a lot of variables for stuff, right? My question is, like that can, because because I actually just found S and A. Because later on I will find S and A. And I didn't bother finding any other P or anything. I just did like that.
I go on behind that.
Oh, can. It sucks.
Sorry, what you say?
This example 14, right? You're under the working that you did, right? You found V and
Yeah.
other stuff lah, which I found. It's a bit strange because I was thinking like